Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Our group were given the task to do the presentation of the future sustainable concrete or brick for project 1 under the subject of ECS 246, Civil Engineering Materials. The slides were prepared by me, Nur Adik Kamila binti Kamarudin, and my other friends, which is Nur Atira binti Isha and Nur Amira binti Samsudin. For the introduction, the concrete is the most widely used building material in the world thanks to its versatility and durability. However, producing cement, the concrete's binding material, is a time-consuming and energy-intensive operation. The objective of sustainable is to minimize the effect of a built facility on the environment over its lifetime. The purpose of the studies is to summarize the study conducted on the use of sustainable materials in concrete mix. For the first article is the properties of concrete containing ground waste cockle and clamshells. Introduction of the article. Seashells from marine byproduct are potentially used in concrete as partial replacement of cement or fine aggregate substitute. In cement replacement, the shells generally have high calcium content, which can affect the concrete physical and mechanical properties. Ground shells is produced by washing, grinding, milling, and calcining to obtain cementitious benefit of calcium oxide that takes part in cement hydration. For the methodology, first, cockle or block clam and marsh clam were collected from local seafood vendor. The shells powder was produced by cleaning, drying, and burning the shells at a brick furnace for 3 days at approximately 600 degrees Celsius. Crushing, grounding, and sieving the shells using the 75 micrometer sieve. A concrete mix consists of cement, water, fine aggregates, and coarse aggregates. The cement was replaced by 4% of the ground shells based on trial mix result. The specimens were prepared by casting the concrete mix in 100 x 200 mm cylinders for compressive strength test and 150 x 300 mm cylinders for tensile strength test. The specimens were cured for 28 days in a water pond and left to air dry. Next is for the findings. As we can see here, the setting time for the OPC clam and OPC cockle were the lowest. This is due to the high calcium oxide content, which will increase the cement hydration reaction rate. And next is for the density. From here, we could see that the OPC clam were the highest. This is due to the calcium oxide content were high and thus reduce the porosity and increase the density of the specimen. Next is the compressive strength. From here, we could see that the OPC clam were the highest. This is due to the calcium oxide content too, which improved the later strength of the concrete. And then for the tensile strength, from here we could see the OPC were the highest. This is due to the bonding strength of the aggregate cement paste. Interface was disrupted by the cement replacement. From the findings, we could see that the OPC clam specimen containing 4% of shell powder produced high initial setting, high density, good compressive strength, and more flexible material than OPC concrete that useful for early strength material in aggressive environments such as coastal area. The utilization of seashell is still not favorable due to its high energy cost for calcining the shells. However, when compared with the environmental benefit of using the seashell waste in concrete, the cost of shells processing for cement replacement is considered cheaper than the use of the ordinary Portland cement in remote coastal areas. For the discussion, there is the critique. The studies were able to handle the research well with all the results supplied, including setting time, density, compressive strength, and tensile strength, proving that cockle and clamshell waste may be used to generate sustainable results. Next, the article's result was persuasive because they were basic, but replete with information. Depending on the size and shape of the specimen utilized for the test, the outcome may be varied. And because the text is brief and there is no accompanying image, the experiment's approach may be difficult to grasp. Next is the cockle and clamshell waste aren't recycled since they are collected. And even if they are collected, most existing material recovery facilities cannot filter them out from the rest of the debris. One way to recycle it is to incorporate the shells into a concrete mix.
Assalamualaikum warahmatullahi wabarakatuh to everyone. My name is Nur Atira binti Ishaq. I'm from Dear 4 EC 1104B1. So, the title of the journal that I have been chosen is Exploratory Study on Partial Replacement of Coarse Aggregate by Teleport Palm Seed. Let's move to the introduction part. So, the increasing demand for construction materials have led to depletion of available resources of aggregates. So, various alternatives for aggregate have been studied and partially replaced, though not fully replaced in concrete making. This study attempts to use teleport palm seed as partial replacement for coarse aggregate in concrete. The seed has no other usage other than to be disposed as waste. The seeds were found to be abundantly available in villages, which was collected and used for this study. The properties of the teleport palm seed were found to be light in weight, very low crushing strength, low impact value, and each seed is 18 mm in size and weight of 4 grams. As we know, concrete, a mixture of cement, fine aggregate, coarse aggregate, and water, is considered as man-made rock, which is the second most consumed substituent in the world after water. The major constituent of concrete is the coarse aggregate, which constitutes about 60 to 80% of volume and 70 to 85% by weight of concrete. Waste material like coconut shells, dead seed, rubber seed shell, palm kernel shells, and etc. were studied by various researchers and replaced for coarse aggregate in concrete making. This study to use teleport palm seed as partial replacement for aggregates in concrete. So, the objective of this channel is the study attempt to investigate the possibility of usage of the teleport palm seed as an alternative for coarse aggregate, which was successful in terms of compressive strength, but the durability factor needs to be studied in the longer term to successfully implement it partially. So the keywords in the journal are aggregate replacement, compressive strength of concrete, teleport palm seed in concrete making. As we can see here, there are two methods to conduct the experiment. First, we must know the properties of the teleport palm seed, which is several experiments have been conducted, which is specific gravity, impact value, water absorption, bulk density, and crushing strength. So, for the second test is compressive strength of concrete. The test that have been conducted is compressive strength test. So, here is the comparison of properties of teleport palm seeds and coarse aggregate that have been tabulated into the table data. As we can see here, the specific gravity of the teleport palm seed is less than coarse aggregate. For the impact value, the coarse aggregate got the highest number of percentage, while the water absorption, the highest is teleport palm seeds, and the bulk density is most highest as coarse aggregate, and for the crushing strength, the highest percentage is for coarse aggregate. So why these 5 activities need to be conducted? So firstly, let's see the specific gravity. The specific gravity is required for the calculation of the yield of concrete. The specific gravity of an aggregate gives the valuable information on its quality and properties. Higher the specific gravity of a material, harder and stronger it will be. So for the impact value measures the toughness of the aggregate. The teleport pump seat, when tested for impact value, it was observed that the seat did not have the tendency to disintegrate it easily. Next is the water absorption. The higher the water absorption property of the aggregate, higher the consumption of water for concrete making. Next is bulk density and crushing strength. So, the bulk density of an aggregate depends on how densely the aggregate is packed in the measure. The shape of the particles greatly affects the closeness of the making that can be achieved. For the crushing strength, the crushing value of the pump seats were found to be very low when compared to the crushing values of aggregates. So that is the method to determine the properties of the pump seat. And after we have determined the properties of the pump seat, now we can move to the second test, which is compressive strength test. As we know, with this test, we cannot conclude that the teleport pump seat can be partially replaced for coarse aggregates in concrete. Yet, the experiment continues with the partial replacement by 10% and 20% of the seats for coarse aggregates. So, the experimental investigation was planned to test the compressive strength of the following proportion of concrete. So, this is the designation of concrete with a table. So, as we can see here, there is 3 designation of concrete, which is divided into 2. The first one is seat used without crushing, and the second is seat used after crushing. The A0 is conventional concrete, and the second trial is conventional concrete. For the A1, first trial is 10% of replacement, and for the trial 2, which is seat used after crushing, is 10% of replacement. And for the A2, it is 20% of replacement for both without crushing and after crushing. The specimens were tested based on the designation of concrete. The mixed design was done according to Indian standard 10260 for M20 grade of concrete. 18 cubes were casted in each designation of concrete for trial 1 and trial 2. The plan was to test 3 specimens each for 7, 14 and 28 days testing. The weight of the materials for each trial are tabulated as follows in the table. So, the table shows weight of calculation of the materials according to mixed design. So, the materials were carefully weighed to correct proportions for casting the specimen for all the trials. The trial 1 designed the concrete were tested successfully without any delays. After casting, the tube were placed in the curing pan for curing process. The crushing of the pump seat was difficult for trial 2. Since the seats were very hard and tough, the crushing of the seat took longer time and various methods were tried for crushing. Successfully, the specimens were casted with the crushed seat and placed in the curing pan. So, before we move to the finding and the result, we must know the problem encountered during conducted the methodology. So, on the 7th day of curing, when the specimen were taken out from the curing pan, it was found that the trial 1 specimen, which is seat used without crushing, developed cracks on drying. The cracks were very intensive, and it was observed that the cracks started to develop at the junction where the seats were present in the concrete mixture. It was important to note that the full seat did not have the tendency to bind with the concrete mixture. As we can see in the picture, the left one is the specimen with full seat, and the right picture is the specimen with crushed seat. The specimen casted with the crushed seat, which is trial 2, did not exhibit such cracks and were tested for the compression strength. Since all the tubes developed cracks in trial 1, they were not considered for further steps in the experimental study. With the first methodology, that have been conducted is the observation helped to analyze the properties of the teleport pump seat. The specific gravity, water absorption, and bulk density values were found to be lesser for teleport pump seats when compared to cost aggregates. The impact and crushing strength were found to be higher for the seats. It is important to know the strength properties of the casted specimen to know the possibility of using teleport pump seats in concrete as an alternative for cost aggregates. So, from the trial 1 specimen, it can be concluded that the teleport pump seats cannot be used without crushing. The trial 2 specimen were tested for the compressive strength and the results are tabulated as follows. So, as we can see, the table shows the compressive strength of the casted specimen under trial 2. The above table shows that when crushed seats are partially replaced for cost aggregates in concrete, adequate compressive strength is obtained after 28 days. The compression strength values of A1 and A2 trial mixes are almost equal to the strength of the conventional concrete AO, which is A0. On comparing the compressive strength between A1 and A2 mix, A1 mix is said to obtain higher values after 18 and 28 days curing. It can be concluded that only 10% of replacement of the teleport pump seats give better results. It was also observed that the tubes casted with the crushed seats were light in weight than the conventional concrete. For the discussion, the above all observations help to analyze the properties of the teleport pump seat as given in the previous data. So, the specific gravity obviously give the lesser for teleport pump seat when compared to cost aggregates. It also follows a specific gravity with water absorption and bulk density. The impact and crushing strength were found to be higher for the seats. So, for the next discussion, it can be concluded that only 10% of replacement of the teleport pump seats give better result. It was also observed that the cubes casted with the crushed seats were light in weight than the conventional concrete. So, in conclusion, the study shows that there is potential for the use of teleport pump seats in concrete material production. The teleport pump seats are also used in making ornament, which is only 25% of the total availability. Almost 75% of the seats are wasted and found to have no use. The study was successful in attempting to find a use for the seats, as well as finding an alternative for replacing cost aggregate in concrete. Teleport pump seat had physical properties such as specific gravity and bulk density, far less in values to that of cost aggregate, but its impact and crushing value are better than cost aggregate. Crushed teleport pump seat concrete in M20 grade attained the required strength of structural concrete at 28 days. The first question is, how well the studies address the research questions? Were there any limitations? As for me, the studies were able to address the research questions well by showing all the results of the test, such as the compressive strength test, and also it provides all the methodology that need to be conducted, especially for the properties of the seats and also the methodology of compressive test. The second question is, how accurate were the results? Any of the results convincing? The result for the article is very compelling by the amount of data that has been provided, especially the data of the compressive test and the curing process. Some of the facts have been also inserted in the journal to make them more knowledgeable. The third question is, what aspects of the research works were unclear? These methods in this article were very short and showing no picture of the test, especially for the properties of the pump seats. It shows that 5 methodology that need to be conducted, but there is no explanation on how we can get all the data of the specific gravity of the water absorption and another. The last question is, how do the studies going to contribute to development of future sustainable product? So my answer is, the sustainability material such as pump seat can be substituted with cost aggregates. This has been proven during the conducted experiments and the result give a positive effects. The replacement by sustainable materials, given the manufacture economical, lower cost and environmentally friendly concrete can be provided. This can reduce the graveling process and helps in keeping the green earth free from pollutions.
From the research, plastic waste material recycling in concrete has many benefits and advantages because it is widely used and has a long service life, which means that the waste is removed from the waste stream for an extended period of time. the scientists discovered new types of engineering such as sustainable engineering and green engineering in order to reduce energy and natural resource consumption. The goal is to minimize negative conditions while maximize benefits to the economy, society, and the environment. Also to reduce the amount of pollution and produce in order to be as eco-efficient as possible. Plasticity has a variety of properties, including being durable and corrosion resistant, providing good insulation for cold, heat, and sound, conserving energy, being economical, having a longer life, and being light in weight. In this research, the main objective is to realize the direct recycling of polyethylene as the green engineering forming technology, also to directly produce plastic cement from waste of polyethylene materials in order to improve the mechanical properties and workability of product. Next, for the methodology, firstly, the polyethylene boards or plastic waste material have been collected from municipal and landfill as a waste of human activities. And then the particles are then cut into small pieces using a special cutting and grinding machine. The result of grinding polyethylene waste is sieving to separate the fine particles from the coarse particles so that they can be mixed with Portland cement and water. And then Portland cement is mixed with the fine plastic waste material and water in various percentage. The percentage of plastic waste that have been mixed is 5%, 10%, and 30%. The percentage of other materials such as sand, coarse aggregate, and water are taken by volume. And then Portland cement and fine polyethylene waste mixed with water to get a homogeneous concrete to cast on the small mold. Sample left in the mold until it dry, then put in water for 3 until 4 days for solidifying and curing to increase their cohesion. After that, samples are left from water to dry and test their properties. The second step was putting the samples again in water for 7 and 28 days to study their stability and the effect of water on their properties. And then all the data of mixed concrete with and without mix of plastic waste has been recorded. For the finding or results, the density of plastic cement produced in the research was shown in table 1. From the table, it showed that the density was decreased as the percentage of plastic waste increased. The difference between them was from 2.6 to 1.6 of the density. For the moisture content, from the table 2 shows the moisture content of the plastic cement produced in the study after being immersed in water for 7 and 28 days. From the result, it shows that after 28 days, the moisture percentage will be lower than the moisture percentage of the plastic cement that was immersed for 7 days. As it stated in the table, the moisture content from the 5% of polyethylene waste to 30% of polyethylene waste, it was 15.9 until 11.4. It decreased. Next, for the comprehensive result, from the table 3, it shows that the yield points for various specimens were discovered to be in the range of 874 to 1,700 Newton after 7 days and 1,155 to 2,000
125 Newton after 28 days. It is dependent on the percentage of the fine polyethylene waste. From the figure, show the compressive strength diagrams for plastic cement that produced by mixing fine polyethylene waste and Portland cement after immerse 7 and 8 days in water. According to the graph, as the waste plastic ratio increase, the compressive strength values of waste plastic concrete mixture decrease at each curing age. It states that the bonding between the plastic particle and the cement paste is weak. Next, move to the discussion. From the result or finding, it shows that plastic cement can be made from waste polyethylene, materials produced by human activities such as food packaging or crates. The result shows that the density of the produced plastic cement differed depending on the percentage of waste polyethylene in the concrete mix design. It is gradually increased by increasing the waste percentage up to 30% and then gradually decreasing. The moisture content for plastic waste was decreased when increased the waste percentage up to 13%. It showed that the plastic waste was dry because it have low moisture content. For the compressive strength, the mixture with 5%, 10% and 30% polyethylene had the highest compressive strength for the product. They have yield points of 970, 797 and 874 Newton for immerged 7 days respectively and 1520 for a mix of 5% and 10% after immerged 28 days. Stress strain behavior is a plastic behavior with multiple stages of deformation. It functions as a semi-crystalline polymer, flexible concrete that is not as brittle as sand Portland cement concrete. As a result, their stress strain diagram show both elastic and plastic deformation prior to fracture. Furthermore, the products containing 5% to 13% waste plastic have good workability and can easily be used to make holes. Even so, as the percentage of waste decrease or increase, the workability worsen and power is generated during the cutting operation. According to the information presented above, the best and most appropriate percentage of waste plastic waste material is 5 to 13%, which result in a mixture with good properties. And in the research, it's still not clear with the durability value of concrete and what will happen if the plastic waste was 100% substitute with Portland cement. However, the solid state recycling process have evolved into a sophisticated and useful methodology for achieving a green state by converting recyclable waste into useful components. The developed process is a typical green forming or environmentally friendly manufacturing process for lightweight materials. It has numerous advantages, including ease of use, cost and energy savings, and clean recycling because it does not harm the environment. To sum up, the plastic waste can be a future sustainable product in construction as its recycling process has many benefits rather than using landfilling or incineration method that will harm the environment.
To conclude all the research, sustainable materials mixed with concrete are the future of products since they assist to save the environment, reduce construction costs, and save energy. The palm seed was used in place of coarse aggregates in the research, indicating that the palm seed has the potential to be used in concrete. The outcomes obtained were satisfactory. Furthermore, the study found that the two types of local seashells were effective at replacing cement in concrete. The content of seashells may be used to predict the development of physical and mechanical strength in concrete. Then, the plastic waste, which had been a problem due to improper disposal, was mixed with cement. It claims that plastic trash might be used to make plastic cement and that the experiment was a success. To summarize the findings, the sustainable material can be used in concrete mixes. This is all the reference. Thank you for watching. Have a nice day.